Hello, welcome to Chapter 1, Module 1. Today we'll talk about solid state devices and how the structure of material have an impact over the material properties. These are the homework questions. I will be posting them as separately. So let's think of a crystal. The most fundamental crystal that we use in our everyday life is sodium chloride. And you have read on it by now that crystalline solid is something that's distinguished by the atoms which are arranged in a very precise periodic fashion. So there is a very fundamental basic arrangement of atoms that's repeated throughout the entire solid. Now, sodium chloride is not a continuous solid, but the crystals, the few crystals that we can read, they indeed show this periodicity in their structure. And the thing about crystal is that it would appear exactly the same if you are looking at one point or you are looking at some other point in the series of those equivalent uh, cubes, if you can call them, or whatever the unit cell. Maybe that's a rectangle, or maybe it's rectangular, or it's a perfect cube, whichever shape. So, and there are other solids which have no structure. So that was covered in other uh, the soft chalk lecture that I posted. Now, in a similar way, every semiconductor material has an periodic arrangement of atoms, and that's what gives specific properties to that material. Now, when you talk about these crystals, the basic definition of crystal is that it is a material which has a symmetric array of points in space. Now, those symmetric points are called lattice, and we can add different atoms or same atoms in on those lattice points inside the material. So, and they may appear in nature, or we may create them like we do solid state crystalline silicon. Now, the location or the placement of those of atoms, especially when you talk about semiconductor materials, those are very important. Now, we talked about sodium chloride. There are other crystalline materials like diamond, but they are not semiconductor materials. So the placement of atoms in a crystalline structure is a property of materials, and then those materials may be conductor, maybe insulator, maybe semiconductor, which is the focus of our studies. But these definitions are all the same. The periodicity of a crystal is defined in terms of the symmetrical array of points, what we call as lattice, and then we have lattice points for all those things. And when we add atoms on those specific points, uh, like we were seeing here in sodium chloride, so there's very specific points for sodium and for chloride. And they all are part of kind of a cubic structure which repeats over and over and over, and it repeats for long distance. Now, keeping that in front of us, we can say, okay, there are atoms which would be added in that lattice point in an arrangement which is called a basis, which can be one atom or a group of atoms. But they would, the condition is they would have all have the same arrangement in space, right? So one corner, another corner. And that's what what we would call, when they are in that arrangement, we call it a crystal. And that crystal is what is of our interest, because that picture which I showed before, what we see is the silicon atoms are placed at precise locations. Now this is a 2D picture, just showing you one layer, but the layer below, which is a few angstroms away, and the layer below, and all the maybe billions of layers, they are all connected to each other in a very specific format. Now, how do we quantify that, their arrangement, or how do they are uh, connected with each other. We define a unit cell. So, okay, unit cell is a three-dimensional thing, but if we were to look at it in two-dimensional, this figure helps us. So what we see here in this figure 1-2 is a two-dimensional arrangement of atoms. Now, in this case, this is a special arrangement. It's called rhombic lattice. Now, the primitive cell here, which we can see would repeat itself, is shown by ODEF. And this is the smallest cell, right? So, but if you look at the picture, we see that ODF can be found everywhere. But if you have to uh, find one such primitive cell, say O prime, D prime, E prime, and F prime, we can always find a vector that can translate us from that position to that other position. So, which means that through some vector displacement, we can always define any cell in terms of the primitive cell, right? We just take integer multiple and that can tell us how far is it from there. So now if we were to, if it was in 3 dimensions, now going from 2D to 3D, we can always find that primitive cell and translate it into 3D space and find a vector that can take us from there, right? So that vector can be a simple uh, vector addition of 3 vectors, each with its own multiple with it. Now, if you do that, so it means that all those cells which form this basic picture shown in 1-2, all the different ones can be defined or explained in, if we define and explain that one basic primitive cell, right? And everything else can be just integer of that. So that's the idea, that's the big idea or the message here, that we choose a primitive cell and we take vectors from there which can define any other part of that big crystal lattice. So what's most important thing for us is to just find out the basic fundamental figure and everything else will fall in place. Now, if I take you back to that picture that I showed, we were using ODEF as the primitive cell, right? Because that's the most simplest cell. But is that the most easy to deal with? It's not the easiest. Easiest would be if somehow we can define something which is uh, more with 4 angles, right angles, right? So it can be a square, it can be rectangle. So here what we see is we see, okay, if I were to take step back and take a look at this picture, PQRS is also uh, a cell which I can see probably is repeating over and over. But the difference here is instead of just 4 atoms and 4 corners, now there will be one atom right in the middle, right? Which is shown as position T in this figure. So instead of using that rhombic arrangement, we can consider a rectangular arrangement also with the lattice point, which has the center at T. So now, okay, this may not be possible for all the rhombic lattices, but the, the point here is that we can pick up a larger unit cell, which is not the primitive cell. It could have been if the figure was all straight in with all the angles right angles, but we can still, instead of using the uh, primitive cell, we can define a unit cell of our own choice, which in this case we can use PQRS rather than the smaller cell. So now PQRS again, the arrangement of repetition can still define this uh, repetition of the letters here, right? So now, what does it serve? It's important to know the unit cell, its dimensions, and the dimension, important dimension is small a, and we call it lattice constant, which is the minimum distance between two atoms. Now, two atoms, what we would call nearest atoms, right? And the nearest atom from on when you go further and keep on going further. So that unit cell has this, for every crystalline material, we have a unit cell, and for every unit cell, we have a lattice constant. So for every crystalline material, we have unit cell and its lattice constant, which would be measured or given in with a variable small a, right? Now, from the unit cell, we can find distance of uh, any other unit cell for that matter. And once we know that, we can find out how far they're apart, and we can find out what are the forces that are acting on them, right? So this is something that leads us to then defining these unit cells for different cubes. And the simplest one is shown the cubic volume. And what you can see here is if I take one front, there are in that 2D front, how many atoms would be there? You have to only include the atom that falls in that 2D. So, and if you're talking about 2D, if you just slice that part in that front square, you would have only 1/4 contribution from one atom in one corner, and from each corner you have 1/4 contribution. So four of them, it will be total contribution in that one square would be one atom, right? Because each one on the edge is contributing just one. We're talking about 2D. Now, if you look at the 3D simple cubic, then what is the contribution of one atom at one corner to that cube? If you think about it, it's only 1/8 of that atom that's being contributed to that uh, cube. How many total are there? There are 8 atoms who are contributing 1/8 of their portion inside the cube. So hence the total would be 1/8 times 8, which will be one atom. So this is now, if I can know how many atoms are contributed in a cubic cell, and then I have the lattice constant, I can find the density of atoms, right? Which would be number of atoms divided by a cube, right? So the volume, number of atoms divided by volume, because that's the way you will have to look at this homework questions to solve that. And of course, if you look at body-centered cubic, then that contribution, you'll add one more contribution because of the atoms, which is right in the middle. And when you look at FCC, which is the third one here, then you have to add the half contribution of each atom in the face as well. So that would make, that would add to the number of atoms that are there in that cube, and hence the density will go up. So, and then we can also find the nearest neighbor. So it's simple geometry. If you pick one atom and you want to, like in simple cubic, the nearest atom is any of those, whether you go right, whether you go up, whether you go left, whether, so because they're all same equidistance. So nearest neighbor is A apart, lattice constant away from that. But now if you go to body-centered cubic, we have to know that there is that atom in the middle. It may be nearest for one atom at the corner, then another atom in the other corner. We can calculate that. We just take the slice, and then it's geometric. We have to lay it out, and that can give you what is the distance between two nearest neighboring atoms. Now, and that's for, if you look at the FCC, the nearest neighbor distance is, it says 1/2 of the diagonal of a face. This is where now you'll take just a right angle triangle. There are two right angle triangles now on one face. You just take one of them and you see there are three atoms on the hypotenuse and one atom at the corner of height and base. So that simple trigonometry will give you the distance, which is half times a square root of 2. And similar way, we can find out the atom which is center of the face, that it would just touch at each corner of the face, the radius of the sphere. Now these atoms we are showing as very precise dots, but no, they are huge. They are filling up the whole region, and that's what is shown in figure 1-4. Basically, they would be packing that cube, right? So hence, this is more realistic way of looking at it. That now, if you know the density, then we will know what is the size of that atom, or how tightly they are packed in there. So